Test, test. Can everybody hear me? Hey, hey, hey. Welcome, guys. I'll start the video in just a few minutes here. First question, how is the audio? Am I coming in too hot, too quiet? On my end, it actually looks okay. Okay, awesome. Cool, cool. Okay, I'm going to do one more tweak to the stream if I can. I'm going to increase the bitrate a little bit. Yeah, it doesn't look like I can. Oh, we'll have to deal with this another time then. Okay. Hey guys, folks. Welcome to the second live stream. Sorry about the loud audio. I'm trying something new here. We're actually routing audio through a wonderful little app called Noise Torch, which actually uses machine learning to clean up some of the audio. So hopefully that'll reduce some of the pops and cracks and like keyboard sounds you might hear. Yeah, so we got some stuff planned for today. Yeah, progressive scan this time. No interlacing like last time. I figured that one out with the help of Matthew Wilson, in fact. But yeah, let's see. Let me turn down the gain a little bit because I am maxing things out a bit. And there we go. Okay, that should be better. So, some updates before we get into any code or anything like that. You may be seeing that there are two screens on behind me. That is actually the V128 prototype that I set up from the last stream. And it's got dual head output. This is actually a brand new feature in Vice Head that I went and hacked in with the help of Blackie Stardust, otherwise known as Blackie on the chat. Yeah, major changes coming and progress in progress, obviously. Yeah, so I'll give you a quick preview of that. So if we head over to the desktop view, you can see if I do start up X128, dang it, there we go. You'll see we've got two windows now. This is in the SDL version of Vice. So if I hit F9X to go over to the VDC, you can then see the output. It works really well. I haven't had any too many problems with it. But we can also bring up the menu. We can change settings by way of these three additional settings. So VDC, VIC2, or dual window. And ta-da, magical. So that's that. And let's see. The other major update, actually, I can't really say there really is a major update. So yeah, so for today, we're going to actually go through... Oh yeah, that was the other major... I'm so sorry. The other major update is that I have the Nibbles and Bytes website back up. So if we go to Firefox, you can see we now have the 6510-8502 opcode list back up and running publicly. You may note that in the URL bar, it is showing as not encrypted. That is unfortunate for the moment. I don't have the infrastructure set up to do SSL just yet. We'll get that fixed again. Hopefully up in July when I actually get a chance to rack the servers and then set up the proper infrastructure. This is actually running on a GCE instance up in Google Cloud. So it's bare minimum stuff, basically just Apache 2 serving a bunch of static pages. We'll get the fancy stuff soon enough. But yeah, today we're actually going to go over the Commodore 128 Tanks game that I wrote a while back and announced on Patreon, but I didn't really do a video on it, so I figured I'd want to cover it today. The code is actually up on GitHub under C128 Tanks. And it's a real simple two-player game. It makes use of the VIC-2. It is designed for the C128. Of course, this could be relatively easily ported to the Commodore 64 since it doesn't make use of any specific features of the 128. I'm hoping to get into specific features for the 128 soonish, especially things relating to the VDC. When it comes to changes in Vice, we've got a few interesting things happening between work from Blackie, DQH, and a couple of others, getting interlacing working in the VDC mode. I won't be demonstrating that today, but once it's a little more stable, I will definitely show this off. But yeah, so I'm actually going to use a presentation for this to make things a little bit clear and try and keep things on track so we don't meander too much. So let me reorganize my windows a little bit so I can stay on task. So the actual 128 source code is not set up for building with Buddy. I know on the main channel I was actually focusing on trying to use Buddy. The reason behind that was that I wanted to try and replicate the 1980s feel of I'm working on this machine and I'm trying to develop in character. But in reality, when it comes to developing on the Commodore systems, it's actually a lot easier to use a cross-assembler or cross-compiler. There have been some very interesting developments relating to that. In particular, on the Discord channel, we have a person that goes by the name of Serenity that has been able to get Rust compiling down for the 6502, which actually produces some really, really good results. So there's some interesting things coming down the pike on that. But for this project, what I used primarily is the Acme assembler. So what we're looking at now is a template makefile that I wrote to convert Acme assembler into a D64 file, which can then be automatically loaded into Vice and then test it. So we can reduce the compile run cycle to a much, much faster cycle. The problem with Buddy is that you're working in the same memory space as the assembler and the editor. And it is very, very common to run into problems where you write a program and then you get like an endpoint off or you miss an address incorrectly, and you end up overwriting either your assembler or your editor and not realize it. And so you actually end up losing source code this way. So by using a cross-assembler, we don't have to deal with that problem. And by using Vice, we can actually do debugging and a whole bunch of other things in the emulator to make things a lot easier on us. Now, in the actual channel, we're going to stay on the actual machine. For the live stream, we'll do some more live coding and transcompiling like this. Sorry, cross-assembling is the actual term. Right, so the Makefile. Let's do a quick rundown on this thing. So basically, I'm just defining a bunch of variables that I can use later. This is a common pattern in Make. You typically want to use a variable because then you can change your actual tool if you need to later. For now, I'm actually using Vice's X128, C1541 to create the disk image. Acme is my cross-assembler, and then I'm using, I'm actually not sure why I'm using LD here. This isn't even used anywhere in this file. So this is actually a linker for a different cross-assembler. The Acme flags here basically just tell it that it's targeting a CBM machine or CBM output. The binaries generated for a Commodore machine are actually very simple. You can actually think of it sort of like a 2-byte load address at the beginning of the file and then the raw binary. So instead of explicitly telling this thing where it's going to, or rather implicitly telling it where it's going to load, for instance, like with a basic program where the load address is assumed, we have to specify for a machine language program what that load address is. And this is why you do the comma 1 in your load expression for most assembler based games and programs, because you're actually telling the Commodore DOS, you're telling it that you want to load a machine language program, and that machine language program, its first 2 bytes are the load address. So for the assembler, we actually have to tell it to set up for this as well. So that's what the FCBM is all about. And then the CPU, obviously we're telling it we're compiling for a 6510 rather than say like a 65816 or something like that. And this last flag tells it to do verbose output, so we can see where the errors are. Yeah, that's exactly what the comma 1 was. Like when I was a kid, I had no clue. All I knew was if I do a comma 1 on a basic program, everything gets screwed up. But that's literally what the comma 1 means. So make actually has this funny thing of doing a double colon target. This is kind of a cheat. Basically, what I'm doing here is I'm creating this phony target called clean that will clean up all the build artifacts, so we can do this later. And then make also has this concept of a pattern rule. Now, all this is doing is it's saying to create a file that ends in the word vice, I need files called, or that end in the word a, end in the word prg, and then this Makefile. And essentially what this allows me to do is I can say make foo.vice, and make will automatically look for foo.a, foo.prg, and makefile.acme. And effectively, this means that if make has a rule for a .a file, or foo.a, or .prg, or foo.prg, it will automatically generate those, or call the routines to actually generate those files for us. So in this particular file, to generate my .vice file, I need a .a, and to generate a .prg, I need a .a. So this allows us to dynamically define how we build the software. Suffice it to say, all this is doing is we generate a vice labels file, which is how we determine where our symbols are. All the labels that we would create inside of our assembler will be dumped into this thing, and then we can use that in vice to use the debugger and put breakpoints at those labels. The other thing is that we generate our assembler, our .prg file, the actual program file, using the Acme assembler this way. And all I'm saying here is call Acme with its flags that we define above, and then output to the left hand of that colon, which is the whatever.prg, using the inputs defined on the right-hand side. So that would be the %.a. And then we have something similar for generating the actual D64 file, which is just a bunch of commands that get piped out to C1541, which creates a D64 file, attaches it, and then writes the program file to the first entry on the disk. And the rest of these are just things to make sure that make behaves itself. We have to mark the .prg, vice, and D64 files as being precious, because make by default will automatically remove intermediate files that it generates when you give it a target. So if I tell it to generate the D64 file for the program, it will implicitly create this .prg as an intermediate file, and it will actually remove that file after it's done creating the D64, which is not what we want, so we mark them as precious. And then final thing is .phony is a special target again, and it just tells make clean is a fake target. It's not actually creating a file called clean. If we don't put this here and we accidentally create a file called clean, make will actually assume that, oh, your clean target is already complete. I don't have to do anything. So you have to put that there, otherwise it'll screw up your targets. So this is kind of like conflating make as kind of like a scripting language, but it gets the job done. So with our actual Makefile, in here, you'll see that we've got a bunch of targets up at the top, and then we've got our phonies here, and then we have this include makefile.acme. Makefile.acme is all of those extra rules that we just defined. So this actually takes a lot of the behavior that we want and makes it generic. So this whole script could be reused for another target without having to change a whole lot. And for our actual target that we're going to build, we create a phony called tanks, and that's just a top-level target we can call to make our tanks.d64 file. Going back to the Acme template, this tanks.d64 just calls this make, which then goes back up to the top make targets up here to generate our results. So when I call make tanks, it actually makes the D64. I have to specify that tanks PRG depends on program sources. This actually calls out to the PRG target here. And this actually will automatically figure out which source files that we need. And you'll see up at the top, I define this variable called wild program sources, and I'm using a Makefile expression called wildcard star a, which is essentially just like doing an ls star.a, and then putting the output of that into the variable program sources. So that way I don't have to explicitly list all the files that I'm going to use. And we do have 3 files, so this is actually helping us out a little bit. And then finally, we have this last fake target called test, which depends on tanks D64 and tanks.vice, and calls x128 with the auto start parameter to go ahead and start tanks.d64 along with our labels and our monitor commands. Cool. So yeah, we also mark these as phony because we don't want to accidentally have an issue where, of course, make gets confused. So there's that. So back at the prompt, we have our tree. And actually, I'm going to use Dured for this so that we can actually see it a little bit easier. And inside here, we've got our Makefile and we've got our Makefile Acme. And then our actual source files are here. So we've got macros.a, sprites.a, and tanks.a. And these are the raw source files. But let's step back a little bit. Let's start looking at overall what we're trying to build. We are actually trying to build a game that uses 2-player joystick inputs to drive little tanks across the screen, and those tanks are going to duke it out. Basically, they shoot bullets at each other, and when one of those bullets hits the other tank, then the other player gets a score point. So it's a very simple, very basic game. We really only need to use sprites in this. We're not going to do anything special with the backgrounds because it's actually a little more involved there. But this should get people like up and running for like how to use sprites, how to actually make a game, how to make all these things work together. So if we head over to the presentation, or rather, if we head over to the source code, excuse me. Yeah. So the base source file is a file called tanks.a. And the first lines of this is essentially just including a couple of other files so that we can actually generate and reuse a lot of the things that are defined in those files. Now, Acme is a macro assembler. Buddy is also a macro assembler, but Acme is a little more flexible, which is why I'm using it. So let's go into that a little bit. So if we go into macros, you can see that I've got these variable assignments, or at least they look like variable assignments. What these are actually doing is we're defining a label that Acme will use later and replace the value on the right-hand side of the equals with every time we use one of these labels, it will be replaced with the value on the right-hand side. So these aren't actually variables. They're actually just, they're static definitions of a value from the right stored in the label on the left. So essentially what I'm doing in this section is I am defining a set of variables that tell us where these kernel routines are. So the kernel has this routine called print immediate, which allows you to print out a chunk of text that follows the JSR instruction that jumps into this routine. Also, there is a cursor positioning routine that we can reuse. Set window changes the overall dimensions of the output device, so we can actually make changes inside a subset of the screen rather than the entire screen. And then we have getChar, which is useful for debugging, but also useful for getting input from the user. We're not going to use this in the actual game, but for debugging, this is actually quite useful to like pause the emulation a little bit and see what's going on and step through things, even without a debugger. You'll also notice that this is inside of a bang adder section. All this does is it instructs Acme that everything inside this particular block is an address definition. And this is important because this is a different kind of thing. We don't want to ever change these values, and we don't ever want to use them in really mathematical what's the term? We want to treat them specially as memory addresses, not as constants. So the ADDR block marks these variables as being addresses. Oops. Then down below, we have a bunch of other constants. So in these particular ones, I'm actually defining a binary value. And instead of using the dollar notation for hex, I'm actually using binary because these are individual bits that we care about, specifically in the VIC interrupt register. So we need to check when the scanline raster has been reached before we can do any work in the system. We need to know when a sprite and the foreground collide, at least in the original. I had originally planned on doing, yes, that is also true, yes. Set window is an editor call, not a kernel call. So I kind of conflated that here because this was early on in some of my work, so apologies. But yeah, so the other bits here are sprite and foreground collide, and then sprite and sprite collide. And when it comes to firing bullets, we're actually going to use sprites to do sprite collisions. And this is actually not the typical recommended way of dealing with sprites. Typically, you want to do a region check or a bounds check because it's faster and more reliable. But for the simplicity of this game, we can actually rely on the VIC2's sprite-sprite collision detection. And so that's what we use for bullets colliding with the other player. And then we also have a bunch of color definitions. This is just shorthand because dealing with color numbers is kind of a pain. And now we're getting into the actual macros. So a macro in Acme is essentially just a way of, yeah, it's a sprite. This is actually just a way of taking a block of assembler and instantiating it into multiple places inside your program. So one of the typical things you're going to need, since we have so few registers that we deal with, we have A, X, and Y, right, is to save those registers out on the stack. And so I have two of these functions, and that's the other thing. When you save your registers out on the stack, you want to make sure you always pop them back into the registers in the same order. If you don't, then you end up with like X in A and you lose a lot of context, especially if you call into subroutines. So what I did here is I created a couple of macros to make this easier on myself that always push things in the same order and pop them in the reverse order. So that way, anytime I have a subroutine where I'm mangling all three registers, I can save them in the same order and then restore them at the end of the function without having to break my brain or get confused. And then we have a couple of other functions down here as well. We have print at. Now print at actually takes a couple of parameters. This allows us to load Y and X with the X and Y offset where we want to print a line of text. We then clear interrupts, and then we call the cursor position routine and then print immediate. So effectively, what we're doing is we're rolling in two function calls into a block of text or a block of opcodes that I can just copy and paste anywhere using this macro without having to think about it too much. So it simplifies the way we work with kernel routines and editor routines and anything in ROM, and even some of our stuff if we decide to use it that way. And then set window works basically the same way. It's just shorthand for working with the set window routine and the cursor position stuff in an easier way, because as you can see, we have to LDA and then LDX and then clear carry, and then we have to call into set window, and then we have to set the other part of it. So we do LDA, LDX, SCC, JSR, then we have to set the cursor position. Like, this is all kind of annoying stuff, and if we had to write this multiple times, kind of a pain. Yes, CLC clears the carry. I'm getting a little too fast and getting a little flustered, so my apologies. Yes, CLC clears the carry. SEC sets the carry. So the set window routine uses this carry bit as a means of determining which corner of the window to adjust, which corner to change. So by clearing the carry, we're setting the top right and the top and the left corner. And then when we set the carry, we're setting the bottom right corner. So you set them both to set your actual window range. And then I have another macro here called reset window, which calls set window and then just resets the window to the appropriate dimensions. You will get a demonstration of the game. Yes, you absolutely will. And then finally, we have the sprite line routine. And I wanted to go into a little more detail on this one because it's kind of compact. If you recall, the sprite organization in memory is actually stored as 3 bytes for every row. Now, in Acme, the output into, rather, the variable into a macro doesn't have a specified size. So what we can do is we can actually create an arbitrary value of arbitrary length, or a value that would span 3 bytes, and then shift it around to actually fit into 3 separate bytes. And so what we're doing in this macro here, this game is, the code here is for a game called C128 Tanks, and that is over on GitHub under my username, JTGans. So if we open up the web browser, you can see here, and here's the URL for it up at the top. But going back to the macro, essentially we're just shifting the bits to the right by 16 for the first byte. Then we do it again, 8 bytes, and then mask it off. And then finally, we do it for the last byte and mask it off. So when we actually use this in our sprites, we have a set in here starting at 0E00 hex. And that's essentially where the Vic2 looks for all of its sprites. This is configurable, but for this game, we're not messing with that. We're keeping it real simple. And you can see we're using the macro here with a binary value that spans over 3 bytes. So we can actually see what the sprites look like in source. So you can see down here that we use the hash character, and Acme allows us to use hash characters instead of like 1 characters. You could use either. Hashes and dots is easier to see, so that's why I did it this way. And this is not my technique, by the way. This is actually done by the Acme author. The macro was actually their invention, not mine. We're just using this for now. But essentially, we just define all our sprites here in the source. And you can see the bullet is taking up an entire shape. But yes, the shapes are visible in the source. Okay, so that out of the way. We'll go back to the source code. And I'm actually going to switch back to a terminal. And when I gave this talk, I had a separate branch for each step in developing this thing. So what we're going to do here is we're actually going to step through the source code as we write it. But we're actually not going to write any source directly, because this is already done, and the game actually already runs. So just as a quick demonstration of what we're building from the start, if we do a make test, we'll automatically switch over to Vice, and then the game starts. And now you can see that we have a score in the upper left, we have a score on the upper right, we've got our player 1 tank, and if I move my joystick, which is a fancy little joystick here, it's not going to work because it's disconnected. Okay, if I use the other fake joystick, which is using the arrow keys, you can see that the sprite moves around. We can shoot. Obviously, there are some bugs, but I will leave those as exercises for the for you guys. And I'm having trouble with the second joystick, so we'll probably have to deal with that later. But effectively, both players can move. We can move them around. They can intersect, and nothing happens. That's important because we do use sprite collision detection, so we have to make sure that we're looking at the right sprites. And then also, we can shoot the other player, and our score goes up. You'll also notice that the red player got a score, and the blue player got a score. There are some bugs in this code. But it should be a good starting point, so that's kind of the whole goal of this. So let's go back to our first branch, which is step 1. So at this point, we have our tanks program. And the first thing we want to do is we want to provide the infrastructure to start our game automatically. And part of this comes in the form of a basic program. So, I'm just trying to be... You could say that, yes. So, basic programs start in the address 1C01 on the 128. So the first thing that we do is we specify this star equals 1C01. And this actually tells the assembler that we're going to start outputting code at that address. Yes. And effectively, since we're working in an assembler, we can't write the basic program ourselves. We actually have to write it in a tokenized form. And this is actually getting into like how the basic interpreter works. But the first part of our basic program is a pointer that tells the basic interpreter where the end of the basic program is. So here we define a word, and in Acme assembler, a word is just a 16-bit value, or 2 bytes. So this is a pointer to the label end of text down below. And we don't want to think about where that actual pointer is, because this program could change size. And that's actually the advantage of using an assembler. You don't have to think about all the explicit addresses. You can let it do all the calculations for you. So that's why we're doing it here. And yeah, it will be in little endian, which means that the most significant byte will come, I believe, I always get this confused. It usually comes before. Is that right? We can look at it in the editor later, rather in the debugger later when we do a memory dump. But the first, or rather the next part of it is actually the line number. And line numbers in BASIC are stored as a 2-byte value. Yes, LSB first, then MSB. So yes, thank you. I can never remember that. So you have to realize I normally work in C and C++ and Rust. So generally I don't think about the ordering of the endianness. I let the compiler deal with it. But that's a whole other level of abstraction that we won't have to deal with. Rather, that we don't have to quote-unquote deal with. Instead, we have to deal with the endianness directly. But basic line numbers are actually stored big endian. They have the most significant byte first, which is kind of backwards. So that's why to get line number 10, we say 000A instead of 0A00. So this is effectively our first line number. And immediately after that, we then include the text. We include the token 9E, then the PETSCII string 4864, and then a null character, or 0, at the end. And this is actually kind of different than what we did before, because we're saying PET. And the important distinction here is that PETSCII is not ASCII, which is also not UTF-8. And the trick here is that my program code here is actually written in UTF-8. So we have to use the PET command. I don't know if they call it commands or macros or specifically what it is, but we have to use this PET command. Tell it specifically that any strings inside this list are supposed to be translated into PETSCII. Otherwise, this 4864 won't actually show up as the right characters. And the 9E is the basic token for the sys command, which is why we don't have the word sys here. When we write a basic program this way, we have to make sure that it's pre-tokenized. Otherwise, BASIC won't know how to run it. And then the end of our program includes a 00 at the end of it, which is a special token for BASIC, telling it this is the end of the program. So this gets all assembled at 1C01. So when we go and load the program manually, and in fact we can do that right now. Oops, wrong terminal. And test, or make test. And I'm just going to reset the machine. And then we can look at the program directly. Oh, there's the dual window behavior. So if we do deload star, and then we do a list. Oh, did I do something wrong? Catalog. Let's try load. Thanks. There. So offhand, I'm not sure why deload didn't load it properly. There is a difference between deload and load. This is actually something that we've run into with Buddy. If you don't load Buddy with deload, it won't actually work. But effectively, you can see now that our basic program is sitting here at sys, rather in memory, at the location we assembled with line number 10 and then sys4864. So I'm going to kill that, and then we'll get back to the source code. So the next thing we do is we set up a whole bunch of additional pointers, rather labels with addresses in memory, so we can handle these things down in the code below, make things a little bit easier on ourselves. And then we get into the actual init routine. This is our main entry point. So when it comes to this address in the basic program, 4864 is actually the decimal equivalent for the address 1300. And at least let's double check that one because I don't want to be called out. So we're gonna have to set the %x 4804. And no, that is actually incorrect. Okay. Game start. So there is a routine in here for actually doing the start of the game, and I'm just missing what the actual address is. Suffice it to say, this does actually start the game at this location here. So the decimals are probably wrong, at least in terms of my mind, but you can assume that that is correct. Let's see. So the first thing we do is we define this macro, and one of the things you can do as an optimization pass is you can make use of macros to do a whole bunch of initializations and fast code by copying that code multiple times in the same location instead of using, like, say, a loop. This is called unrolling a loop. And in this case, I just did this as a shorthand. We define a macro to initialize our sprites in the vic2. So the first thing we do is we set up our sprite pointer. So we load in the shape pointer using this variable here. We divide it by 64 because when we're dealing with this in the vic, we're not using a full pointer. We're actually using a truncated pointer for the vic to get the actual pointer in RAM. And then we store that at the sprite pointer vector in RAM, offset by the sprite number. Then we can set our color. So we load in the color from the macro as an immediate into A, and then we store that at the color location in the color. I don't want to call it a vector, but it's an array for the colors of each of the sprites. And then we set the sprite position. You'll note that I'm saying stride is 2, hence the multiply. This is because in the location array for the vic2, it's always sprite1x, sprite1y, sprite2x, sprite2y. So you can think of a stride as like the number of elements in each one of those things. So I'm multiplying the position by 2 to make sure that I skip every other byte when I'm writing to the RAM. So we load the x and y, and then we set its facing direction. Now this is not a vic2 register. This is actually something that I'm dealing with as a way to determine which sprite is showing and to determine which direction to send the bullet when it's fired. Because normally we won't know which direction the user is facing, and so we won't have any idea of where to send the bullet. Yes, it does look like C64 stuff. This is actually very similar to C64 stuff because the C128 is actually a superset. So it still has the VIC2, it still has the 6510. So it's going to look very similar. And this particular game uses mostly the same stuff that the Commodore 64 had, because I was looking for the simplest possible game to come up with so that folks can follow along. So now that we have our macro, first thing we need to do is we need to turn off decimal behavior. So we do a CLD. And that's because we do a lot of math with the sprites, and we don't want to end up just dealing with BCD math, which will actually reduce the results that we get into base 10 rather than base 16. Next thing we do is, because we're running with basic 7, unlike a Commodore 64, basic 7 actually has a bunch of interrupt routines that are built into it so that you can do things like have sprites move along the screen at various vectors. So we have to disable those basic IRQs. And you do that by storing FF on D8 in the 0 page, and then also 12FD elsewhere in RAM. Yeah, I mean, there is actually one use for BCD features, and that would be for scorekeeping. It actually would be a good way to generate the additions to the score registers, or rather the score values in RAM. I don't do that in this program, but that could be used to display a score value on the screen. Because ultimately the score values are not actually used by any part of the program generally. It's usually just a value that's displayed on the screen, so you can kind of shortcut it that way. Right, so the next thing we do is we then disable basic, we leave the I/O region, the kernel region, and the character ROMs mapped into RAM. Now this is something that you have to do in a slightly different way on the Commodore 64. You're actually changing the way the PLA behaves on that machine. In the 128, we have to modify the MMU so that we can access just the areas that we want. So in this case, I do this only once, just with a simple LDA and then store to the MMU control register. This is not an expensive operation. This is actually pretty easy and quick. So it is actually possible for you to manipulate this all the time inside of a program. And in our later games, we're going to make use of this to use the extra amount of RAM that we have stored in the machine. Because remember, we've got way more than 64K. We have 128. Technically, we have 128 plus 64 because we have the VDC's RAM that we can sort of crib on as well. But that's going to be in the future. So first thing we do is we do this clear text screen thing. You may have noticed that when I ran the game, we had that fancy fade out routine, and then we had that like the character spinner. This is kind of just a fancy way of making the playfield clear. Yes, he does do a video on BCD. Highly recommend Robin's video. It's an excellent introduction on how to use BCD. So the clear text screen routine is really, really simple, and it's kind of just a fun little effect. So if we look for that, clear text screen, it's a very, very simple routine. And let's see, do I have something useful to talk about in the presentation? I do. So yeah, our first step in the game, excuse me, is to clear the playfield, because we don't really have any obstacles to get in the way of the user. We don't have any things to interrupt the movement of the bullet. Those are enhancements we can get on later. But for now, we just have an empty playfield. So the algorithm is very simple. Essentially, we just load in a character byte into A from its location in screen memory. We compare it with the space character, which is screen code 20. And if it's greater, then we skip the decrement and instead we increment. And if yes, VDC access is very slow, but we'll get to that later. And then also this will have an immediate effect because we're actually changing screen values in RAM for the VIC-2. And if you recall, the VIC-2 is running in parallel with the 6510. So when we change its RAM directly, we're actually changing the screen directly. And so that's how you can end up with a real fast, fancy fade out. So going back to the code, our clear text routine, first thing it does is it loads X with the value 0. So we're clobbering X, and we're making use of that that register in this routine only. We then also have a macro, an inline macro here that I'm defining specifically for this routine to make the decrement or increment a little bit simpler. So not all of the characters are going to be, well, let me start again. When we do this clear routine, this spinning effect, we want to make it as short as possible because when you're iterating through 256 characters, that can take a while. So in the, just as an FYI, in the 128, the machine that is in here, the CPU that is in here is the 8502. It is not the 6510. The Commodore 64 actually uses the 6510. Effectively, you can think of the 8502 as the brother to the 6510. The ISA, the instruction set architecture and its registers and all that stuff are effectively the same between the two chips. The only difference is the pinout of the chip itself. So I believe the 8502 has a couple of extra I/O pins that they can use to manipulate things in the hardware architecture of the 128 that the 6510 does not have. But I would suggest checking on Wikipedia for info on that, because the difference is really quite minor. Yeah, so back to the code. Essentially, we're trying to find the midpoint on the character set, because we don't want to iterate from 0 all the way through the character set. We just want to replace the characters on screen and move them to a blank character so that the playfield is clear. So we load in the screen character, we check it against the space character, we then branch if it's equal to, and then we then either snap it to character 127 and then go down, or we just move on. So effectively, we're going through each section of the VIC2's character RAM multiple times here. So the macro actually allows us to easily deal with the pages of RAM in a loop in a faster way. So each time we go through this loop, we're effectively getting and setting in 4 different places in the VIC2's character RAM, or sorry, screen RAM. So we do that for 4 times, then we increment X, and then we go back to our loop if we haven't finished. And we do this 256 times. And then we also have this deck to 0 macro, which will then load from the address. It will pair with the space character, and if it is equal, then it will skip over the decrement. Otherwise, it will just go ahead and decrement the character down to the space character. So then we load here. Here's where we're actually doing the decrement routine. So let me start again. We're actually going from a middle character in the character set either to the left-hand side, so like to 0, or in this case, character 20, since that's a blank character, or we're going out to 128. Yes, that is correct. The C64 is a 6510 machine, not a 6502 machine. Yeah, there were many variations on the 6502, and all of them having all kinds of different model numbers. And effectively, the core itself has never changed. It's always been the same ISA, the same instruction set, the same set of registers, the same general behavior, but the I/O pins changed between them. And that's because as time went on, we changed our technology, right? So we went from SRAM to DRAM. We went from I/O pins on I/O expanders to integrating some of the I/O pins into the chip, and the behavior is basically the same throughout all of these variations. Exactly. So yes, he has. Also, I highly recommend joining our Discord. Bill Hurd is actually on the Discord and is actually answering questions there. So if you do have a question about something, good place to ask. But try not to overload him, of course. So yeah, essentially, all this is doing is just moving from the center down to 0, or the center up to 128. And then once that's done, it then returns to the previous color, which then produces that spinning effect. So after that is complete, we then fade to black. So the first thing we do is we fade all the characters to a blank screen, and then we fade the colors back to black. So we JSR to fade to black, which is down here. And this is just a simple set of tables that we walk through with a short delay so that it looks like the color is going from the green and gray down to a full black. And these are hand-coded as a set of numbers at the beginning of the program. At the beginning of this little sub-program. You'll note that the label is here for fade to black. This zone section doesn't actually have any effect in the output of the source code with Acme. Effectively, all it's doing is telling Acme to tell us where an error has occurred in the source code for easier understanding of where exactly the problem is. So if I write something incorrect inside this particular zone, say like, I don't know, a non-existent opcode like ASDF, it will tell us specifically that there is an error in the zone fade to black at this particular line. So it makes it a little bit easier in trying to understand the output of the error codes. But essentially, we have our border colors, which go from 15 to 11 and then 0. I believe this is going back to our colors. See, these should actually be these colors. We're going from light gray down to mid gray, then to dark gray, and then 0. And then the background does a similar transition. So it's light green to light gray to dark gray, and then finally to black. And the way this actually works is we load X with 0, and then we have a loop where we're using X as an offset. So effectively, we say load A with the value at border, which is here, offset by X, so that we end up loading each one of these in turn as we go through this loop. So some native assemblers did. There's an excellent set of articles that showed up on Hacker News that I don't have the link for. Commodore went through several variations on their own assemblers, starting with just a raw assembler, and then eventually moving to more of a macro assembler for the 128. So the 128's ROM is actually built using a macro assembler. The 64's ROM, I'm not 100% certain if they did. But some of them started out with just raw. And no, that is not you. That is actually the video stream as well. I keep getting warnings. Unfortunately, there's not much I can do about it. So we're just going to have to keep going. Apologies. The routine here. Yes. And that is the only assembler I had for the longest time as well. Buddy actually is a macro assembler, by the way. You can do these kinds of macros in Buddy. It's a little more awkward for its syntax, and that actually stems from the fact that it's running on the machine. It can't process strings all that great. But for now, we'll use Acme, and then we'll get into Buddy a little bit later. But essentially, we're just loading in the border and the background colors in order using offset notation, and then storing them in the BG color and border color. And then we continue doing that as we go through this loop. And then if we've stored a border color that ends in 0, then we jump down to the plus down here and then exit the routine. So we're actually using the 0 in these lists, both as a color and as a notation that it's the end of the list. And then we have our busy delay loop. It's very simple. We're not doing anything special with raster delays. We're just loading the value 100 and then jumping to this routine called busy delay. And busy delay, we go to it, is really simple and frankly a little bit inefficient because we save the registers and the restore registers. And we're doing that for all 3 registers at the beginning and end of this thing. But it's a delay loop, so that's okay. And essentially it just goes through this iteration loop, doing nothing for however many times that we specify in the Y register. I'm going to have a hard time trying to find that again. Okay, so once we're done with that, we increment X. That moves us down the list. And then eventually we then hit the RTS. And then our screen is now black with nothing in the screen. And we can actually start showing the real setup, which includes the 2 characters. So going back to fade to black. Okay, so we JSR fade to black, and then we set up our sprites. So the sprites here are using that macro that's up above. And essentially all I'm doing is I'm telling Acme that I want to initialize sprite 0 with the sprite tank down. So essentially, if we go over to our sprites, you can see we've got tank down here. So this is just a block of data. And effectively, all I'm doing is I'm telling the vec, please use this shape for sprite 0. And then I'm also setting a tracking variable elsewhere in the program that specifies which direction this player is facing. And I'm saying he's facing down. And I set his color, so this actually goes and changes the sprite 0's color to red. And then I set its position to 0, 0, which is not actually screen raster coordinates. These coordinates are translated. So effectively, 0, 0 is going to be the upper left-hand corner just inside the actual playfield, so outside of the border. And I'll get into that how that works in a moment. Then we do the same thing with sprite 1. And then we want to initialize the rest of the sprites as well. So we do this Acme extension. We're doing a for loop. And effectively all we do is we say, we've got this variable called I, and we want to go from 2 to 7. And then I want you to repeat this block of code with the variable I replaced with the incrementing value. So it works kind of similar to a C for loop. But effectively, we're just calling init sprite. And we're initializing all of our bullets in this array with all of their locations, their sprite pictures, which are set to 0 at the moment, and then the color black. And then we also set their Y locations as a debugging step so that we know that the sprites are actually initialized. Then we turn on all the sprites. So we set the sprite enable register to all Fs, and then we jump into the game loop. So the game loop is pretty simple. So we've got our game loop routine here. So we start here, we jump into this, and we're using an unconditional jump because we're always going to be in this. There's no way to quit the program. And then we have this other thing called update sprite positions. And this gets into how we calculate the sprite position on the screen. Apologies. So update sprite positions works kind of in a funny way. We go over to our web browser. The sprite data is very simple. So we're dealing with 24 by 21 monochrome pixel data, which is why our sprites look the way they do in the source code. And the X and Y are in raster coordinates. Now, raster coordinates actually go outside of the border. So if you consider that this is the actual screen that we're working with, 0, 0 is actually up in here. And this would actually obscure the sprite entirely. So we have to offset our playfield a little bit. And so we do that in the update sprite positions routine, but we also change the way we deal with X coordinates. Because remember, we have that seam that we're dealing with. We only can store a location in the VIC2 using 2 registers. We have the least significant bit, which goes from 0 to 255, and then we have the most significant bit in another register for each sprite. So we have to calculate that position in X in a different way. But that makes it a pain to figure out where that sprite is being positioned. So instead, what we do is we just assume that the playfield is actually divided from 0 to 255. And then we do a calculation each time we do an update into the VIC registers to offset and then expand the values into that extra bit. And we'll get to that in a moment here. So, let's see. Yeah, this is a sprite positioning. This is actually the thing I was trying to get to. So the X and Y coordinates are specified in terms of raster lines and pixel clocks, right? So they actually go from 0 to 50, and that's all part of the border. And then it goes down to 250 for the Y coordinate. And then also going horizontal, 0 is still inside the border. It goes up to 24 before we actually get into the playfield, and then extends all the way out to 320. Obviously, that's too big. So we've got this seam at 255. So we store a 9th bit, store the larger coordinates. And in our setup, we're going to transform this. So instead, we're only going to use 8 bits as an offset for the border. So the 8th bit is left shifted into the carry to be the 9th bit. So you can think of our X position, which is going to be from 0 to 255, right? We're going to add 24 to it to push it out of the border on the left. And then we're going to divide it by 2 and then left shift by 2 to get the actual Vic coordinate. And then the carry bit is then our most significant bit. And then for the Y coordinate, all we have to do, since we're not dealing with this extra expansion here, is we're just going to add 50 to it so that we can get to the outside of the border. So going to the code, updating the sprites, like we have this sprite position value, and we're storing this sprite position value in a different location in RAM. The sprite position value is actually going to be 0 to 255, like I said before. So when we do our updates, when we change the position of our sprites, we're not changing the position of the sprites in the Vic register directly. We're actually changing it in a shadow location in RAM. And then later, when it's time to update the sprite, we then run this routine, update sprite positions, to transform the coordinates and then push them into the Vic registers. Why divide by 2, then shift by 2? Doesn't the shift undo the divide and then you end up multiplying by 2? Yes, I believe that actually may be a... I believe that is actually a typo, because we... in X, LDA, DLC, then we add with carry, 24 divided by 2, and then we shift MSV to carry. I am spacing how this works. I wrote this a while ago, so I'm actually spacing why we're doing the divide by 2. This may be because the center of the sprite is offset. Is that correct? So I am looking through the manual here right now to double check this. Yes, that's actually incorrect. This is we're doing an arithmetic shift left, which is actually taking the yeah, I don't think that's correct. Enabling a sprite, data pointers. This is not what I'm looking for. Right, so these are X and Y positions here. That's okay. No, you're totally right. This is actually what I go back to in Discord, and then even on the actual channel. I want you guys to change to correct me, because what I say is I'm not infallible, right? Like, I work in a lot of different systems, and sometimes I forget. So one of the problems we're running into here is that I wrote this several months ago, and I'm actually forgetting most of the context that was in my head. This is actually a technique that Shalon 4K or 10K, I can't remember, but Shalon uses in his live streams as a way to deal with this this aspect of that seam and deal with sprite positioning a little bit easier. Yeah, so here we're actually saying that the offset is 24, and then the lower half is for Y is actually 50, which is correct. Offhand, I'm spacing Y. I'm doing a divide by 2 here. This may be unintentional ASMR. I'm getting closer to the microphone, so that's probably the reason. But yeah, I will have to get back to you guys on that one, because I am totally spacing why we're doing a divide by 2. In theory, this should just be a add 24 to get this offset. And offhand, I'm just not really sure. The code actually does work, though. I will demonstrate that right now. So if I do a make test, and then we switch over to Vice, you'll see that once we do the screen clear, the sprites are in the correct positions. So this is actually our offset 0 by 0. And yeah, what's this? Going during the 80s Contron box? Yeah, because we're only shifting once. You need to add half if you're adding before the shift. Yes, that's correct. Thank you. That is absolutely correct. And then we ASL, and that's the result. You guys are absolutely correct. Thank you for the correction. Right. Yes, and this happens with me too, especially when I'm writing raw assembler. If I don't have a full plan in mind, I will often end up writing code that is actually inefficient or otherwise confusing. And I believe that may have been what's happened here. Yeah, I think the slide is actually incorrect as compared to this. And those slides actually are the same slides that I used when presenting this internal at Google, because I did a presentation about this as well. And I just haven't had time to do this properly with you guys, so apologies. But essentially, we store the MSB in the stack for later because we're going to use this again once we've done this calculation. So then we update Y, and so we increment X because we're using X as the offset in the sprite position array. This is again X and Y. So we want to increment X so we can get to the Y value. We load that in A. We clear the carry bit, and we stored that earlier. And then we add 50, and then store that as the sprite position in the register. And then we move on to the next pair. So we compare X with F because we only have 16 of these position bytes to update in the register. And if we haven't reached the end, then we go back to the beginning and we do the next pair. Now, once we've updated all the positions in the VIC2 register, remember that's only the least significant byte of this location. We still have to update the sprite MSB. And so what we're doing here is we're then pulling the sprite MSB off the stack, and then we're storing it in the sprite X MSB. And this is actually kind of a trick here. I do work at Google, but Google is immaterial here. So what I'm doing here, this is the thing I wanted to cover. So we're actually accumulating bits as we update the sprites. So we add 12 in this, or sorry, we're adding 12 to the X location. Then we shift the MSB into the carry bit, and then we store that in the VIC2 location. We then pull A off the stack. And I think this is actually where one of our bugs is, because this is the other problem. Because we're pulling A without prior to this pushing A onto the stack. So it could be an uninitialized value. We don't know what it actually is. So we pull A off the stack, and then since the MSB is in our carry bit, we rotate it right into the left of A. And then we push A back onto the stack. So each time through this loop, we're going to pull A off the stack, we're going to rotate the carry bit into it, and then we push it back onto the stack. And we'll do this 8 times for the X values, and that eventually produces an 8-byte, or rather an 8-bit value, which we can then use as our sprite MSB for the VIC2. So this is doing a little bit of trickiness with this rotate routine. So once we've got the MSB, we then store it, and at that point we have updated the VIC2 with the actual coordinates using raster coordinates from our other coordinates. Yeah, so yeah. And again, this is actually a technique that Chelan uses quite a bit. I've never used it before, which is why it's a little bit clunky, so apologies. But this is what we do when we learn, right? So this is about as simple as I could make it. So update sprite positions is just being called at the frame start, and this is all we do. So our first step is to show these sprites on screen, get the coordinates working, and then initialize all of our sprites. So when we run this thing, going back to our terminal, and then make test. Here we go. And so here's our sprites at the right locations. Of course, if we try and use the joystick, nothing happens. And that is because we don't have anything else actually working here. We're just setting up the display. So that's it for step 1. The next step is we have to start thinking about, yes, we are actually working on an actual game. So this is just the first step. So if we look at the branches, we've got 5 steps in this whole development process. So let's get up to the next one. So we're going to move up to Tech Talk step 2. I got a stash. There we go. Right, so our code has not changed all that much, but the next step we're going to do is going to occur inside of our game loop. So our game loop, there's actually 2 things here that's happening in step 2. The first one is we're dealing with interrupts. So we actually want to plug into the raster interrupt routines coming from the Vic. So when we start talking about this, I'll switch back over to the presentation again. We want to make sure that we update the sprites at the right time, because if we don't, we're going to cause tearing in our output, and things will also just run too fast. So you have to think about it from the perspective that we're dealing with 2 cores. We have the VIC-2, well, actually technically this is the VIC-2E, it's a different chip compared to the Commodore 64, functions the same way. I was actually planning on doing an hour. If people want to keep going, we can. Or we can put it off until next weekend, and then we'll do another live stream. We can do the next few steps. What are people thinking? Because I can keep going. I'll leave it to you guys for a moment. Keep going? Okay. Yeah, okay, we'll do one more step, and then we'll hold off the rest for the next one, because this is actually going to be pretty involved as well. Okay. All right. Let's do this next step. So we're dealing with interrupts, right? So we want to make sure we don't do this too fast. If we do this too fast, because the 6502 is running at 1 megahertz, the VIC-2 renders each frame at 60 hertz. So this is way slower than the 8502 is making changes to RAM. So if we just have the 8502 sitting there and updating the sprites all the time, we're just going to change those things too fast. We're going to create this tearing effect. And, you know, if our sprite here is this little plus, like our bullet, the VIC-2 is going to come across as we're running, because both are running at the same time. It's going to come across to about here, and we're going to change the location of the sprite. So we move the sprite 5 locations to the right. The end result is that we end up with a half-finished sprite render, and then when the Vic finally makes it over to the actual location of the sprite, we end up rendering the sprite again. And so we end up with that tearing effect. And we want to stop that. So we use the raster interrupt to trigger our sprite position updates off screen. And this is called racing the beam. Essentially, we're going to wait for the raster routine to reach the end of the screen, and then we're going to update our sprite. We're going to wait for the Vic to reach the end of the screen, and then we're going to update our sprite positions. And so the next time that the Vic goes back up to the upper left, all those sprites will be in the updated position. So going to the source code, our game loop does change a little bit, but the most important thing is actually our interrupts, or rather our init routine. Besides setting up the sprites, we want to wedge in our interrupt routine to handle this interrupt notification from the VIC-2. So we call this wedging because we're actually taking our routine and we're pushing it into the call stack, right? So the VIC-2 will interrupt the 8510, or sorry, the 8502. There I go again. 8502. Okay, I may have the term wrong, so apologies. Yes, controlling both screen and code is racing the beam. You are correct. This is not really racing the beam. But you can think of it kind of in a similar way, because we don't want to deal with updating the screen at the wrong time. So we're not racing the position or the calculations of things on screen, because we're not directly driving the screen. We're having another chip deal with that. But we are having to figure out the right times to update things. So I'm using the wrong terminology, but the concept is the important bit. Yes, v blank waiting. That is absolutely correct. Except in this case, we're actually waiting earlier than the v blank because we have the advantage of these giant blocks of border where nothing can be shown, and the Vic isn't going to render anything there that matters for us. So we get that extra amount of time besides just the v blank. So yes, the Vic2 only works with CRT screens. That's actually how it's designed. So wedge interrupt routine. This is a subroutine here that inserts our IRQ handler into the vector address that the 8502 uses when the Vic2 interrupts the 8502. So the first thing we have to do is we have to set the interrupt bit. And yes, there is a bit in an address that can tell you when you are in a v-blank. You can actually query the Vic2's registers for that. In this routine, I'm using an interrupt instead because it's a little bit what I chose to do. There's no particular reason why we couldn't just sit there and poll as well. Both methods are valid. But in this particular design, I'm using the interrupt as a means to tell us when we've reached a point where we can actually update the frame. So the first thing we have to do is we have to set the interrupt bit. And this will prevent interrupts from occurring on the 8502 before so we can manipulate the actual things in memory. And we have to do this here because when we change the vector, when we change that value, you have to remember that the 8502 is using a 2-byte value for that pointer. So it is entirely possible for us to update just the LSB and then have an interrupt just before we get to this point. And if that occurs, then we'll actually jump to an arbitrary location in RAM. So we actually have to disable interrupts and then update the ISR. So in this case, actually, this is the save routine. The interrupt problem would be here. Yes, that is true. IRQ no polling is actually better. It's more accurate, and you can do more other stuff at the same time. I'm kind of going about this as a naive way. We can get into the more appropriate routines a little bit later. So effectively, we save our system ISR. So this is actually saving the previous value that was stored at the IRQ pointer. And then we take our interrupt callback location, and we store that in the ISR location, the pointer. So we have this construct here, this left greater than, the less than sign. This tells Acme to only get the lower byte of this pointer and then load that into the A register. And then we do it again for the high part of it as well. So once we've stored our pointer in that ISR location, we can then tell the VIC, by way of its VIC raster register, we can tell it we want to be interrupted every time the VIC reaches a certain raster line on the screen. And in this case, we're using frame start raster line, which I don't think, yeah, okay, which we've defined as 250. And if we look at our screen again, you can see 250 is down here. So this is down at the bottom of the screen, right at the v-blank point. So essentially, not the v-blank point, excuse me, right at the bottom of the visible viewing area. Right, so this is, at least if we go into the emulator, which I don't have offhand, this would be at the bottom of, I believe this is the bottom of the gray playfield. And so, double check these values here. 250, no, that is at the bottom of the border. Yeah, that is the bottom of the border. That's not the bottom of the gray playfield. This is actually the bottom of the border. So yes, the start of what is known as the front porch in the NTSC signal. So essentially, this is a blank spot in the output of the VIC to the CRT. So once the VIC reaches that line, we want it to interrupt us. So we store that there, and then we re-enable interrupts. And the minute this instruction executes, we can then be interrupted in our interrupt callback, which is down below. Now the interrupt callback, the first thing it does is it reads the VIC interrupt register. Now this is important. This is really important because the VIC has a, the 8502 will re-trigger our interrupt routine if we don't read this register, because the VIC will continuously keep the interrupt line high until this register is read, and then it goes down low. The 8502 handles interrupts in a level triggered fashion, which means that as long as that line is high, it will re-interrupt itself. So we have to acknowledge the interrupt from the VIC, otherwise we're just going to keep getting interrupts over and over and over again in the middle of our own interrupt callback, and it just makes a mess. So we then have to check why we were called on this interrupt, because it could be because of a CIA timer, it could be because of anything else in the system. So we call this maybe trigger frame method. And the maybe trigger frame method basically loads in, it reuses what's in the A register. We're not changing anything in RAM here. We've actually already loaded the reason why we were interrupted from the VIC into A. And so we end that. Yes, I should be disabling interrupts in the ISR and then re-enabling when we exit. That would actually also solve that problem. But we would still be re-interrupted after we re-enable interrupts at the end of our ISR, because otherwise the VIC isn't going to know that we are handling that interrupt, and it's going to keep the interrupt line high. So the minute we exit the ISR, and the minute we turn interrupts back on, we get re-interrupted. So even if we disable that, we still have to acknowledge the interrupt. So we still have to do this trick. And then we AND that with this particular bit, the VIC int scanline bit. And if that's equal, then we just go to the end of it, because we know that if this is 1, then we have not reached our interrupt. If it is, let me double check the value of this one, because I'm spacing this actually. So this is actually defined over in our macros routine, and int scanline, you can see, is actually just the bit 1 in a register of 8 bits, right? So we do an AND operation, and if it's equal, in other words, if the 0 flag is set, in other words, if this bit is not set in the register, then we go to out. We restore the A register because we modified it with the AND routine, and then we return to the caller. In other words, we have not been interrupted for a scanline raster location. We've been interrupted for some other reason, so we don't want to trigger the next frame. Instead, we load A with the FF value, and we store it into another location in RAM called frame start flag. And this is, I believe this might be a 0-page location or something like that. Frame start flag. There it is. It is not in 0-page. These are just globals somewhere else in RAM, basically after most of our code. So this is actually a little bit inefficient, because every time we write to this, we have to use a full 16-bit value. We can't use, or an offset value using indirect addressing. If I wanted to be super cycle efficient, I would put this inside of the 0-page, because then I don't have to do the extra fetch for the extra byte value for the offset. But for now, this is what I'm doing. And so basically I use this as a Boolean to tell me in the other routines that this is the start of the flag. We've actually hit the start of the frame. And so we store that in frame start flag. And then we reset the raster trigger, because every time the raster trigger is fired from the VIC and acknowledged by our program, it will not re-interrupt until we rearm it. So this routine here stores the raster line number back into the VIC register and then will allow us to be re-interrupted the next time around. And again, even if I disable interrupts, if we don't acknowledge it, then even regardless what the fact that we're doing this, it will still keep the interrupt level high because it's never been acknowledged. So just FYI. This is born out of blood, by the way, because for the longest time I was like, why am I continuously being re-interrupted? And it's because the interrupt line was not being acknowledged. So something to be aware of. So maybe trigger frame is essentially just setting this flag that we've hit our raster value. It's the start of the next frame. So if we go back to our game loop at this point, because that's the end of the callback, really. Well, actually, no, it's not. Sorry, apologies. We actually get back here. So we return from our maybe trigger frame, and then anything that's not tightly coupled within IRQ, we go ahead and handle here. In other words, what I'm saying in this comment is not really so much that it's tightly coupled with an IRQ, but more that it is specific to the game loop itself. We don't want to, we want to have time to update the sprite positions once the raster line is at the bottom of the screen, right? Because when we're here, we've got a little bit of time before we actually get back to the visible play area where we can do things like change register values and stuff. And so in this routine, what I'm doing is I'm doing that update. I'm taking those shadow values of our sprite positions, and I'm copying them into the VIC2. And we can do this right now at this point because the raster line is here and we've got the border that we're going to draw next. So we've got some time before we actually start rendering the real playfield. So we should use this time to update the sprite positions. And so that's what we do here. We copy those values into the VIC registers, and we can do that safely without messing up any rendering. The next thing we do is we then call cycle bullet colors. This makes the bullet colors, or the bullet sprites, stand out a little bit so that they don't look like, well, they don't look static. They don't look like they're anything unspecial. It gives it that extra level of pizzazz. So I am not saving registers at the start of my ISR. That actually, so the ISR routines are a little bit funny. What we are replacing here is actually a little bit further down in the stack. So we're not actually replacing the global interrupt routine. We're actually replacing just the vector, or sorry, the raster part of it. The global interrupt routine is actually in ROM, and that I'm having a hard time remembering if that actually saves and restores the registers. That may be the source of some of our errors. We may need to actually save those, but I'd have to double check the ROM code because if I remember correctly, the 8502 does not save registers for you, but I don't remember whether or not the 128 actually stores registers for you in its routine. So we should double check that in the next live stream. I'll have an answer for you. But for now, in fact, I'm going to mark that down in a to-do so that I don't forget and we can actually answer that. We do have a macro for saving the registers, but as you can see in the interrupt callback, we actually don't call it. So that may be actually an error. Okay, so I'll remember that for the next one, and we'll double check that. Yeah. So the other side of the coin is interrupt callbacks are kind of tricky because, again, going back here, we have a very short time between line 250 and line 50 to do our work. So everything inside our interrupt callback needs to be as short as possible. You don't want to have these things do a whole lot of work, because otherwise you actually could end up making changes out here inside of your viewing area. You don't want that. Or you could actually miss your next interrupt even. So you still need to make sure that you deal with that. As for PHA, PHX, PHY, in the 8502 opcode list, you can see all we have for pushing and popping is PHA and PHP. It would be nice if we had PHX and PHY, but most assemblers will emulate PHX and PHY as the macros that I actually define elsewhere. But really, the only way you can push something onto the stack is by way of the A register. PHP and PLP actually just push the processor status register. So that's like our overflow bit, our carry bit, all those other things. That's being pushed. So we actually can't control that. Instead, we can only use PHA and PLA. So let's see, where were we? We were talking about the game loop, or were we calling? Oh yeah, it's the interrupt. Sorry, the init. Sorry, the init routine wedges our interrupt routine, then jumps into the game loop. The game loop, then down here, at the start of our routine, we're using the bit command or opcode to check our frame start flag. So this is just going to load in the value, or rather, set our sign bit based upon the value that's in this location in RAM. And it's comparing using the value that's in the A register, which may also be a bug. So that's something else we need to think about here. But if the sign register is positive, in other words, we're not negative, as in like the sign is clear, then we jump to our actual, like the start of our loop here. So this is essentially just a busy loop. It's not doing anything until we hit the start of our frame. Once we've hit the start of our frame, we clear the start of the frame flag. And that's the first thing we do because we don't want to immediately go back in and rerun in the middle of a frame. And then we go into the start of our frame. And for now, we're actually not doing anything with it because the focus of this was to make sure that our interrupt routine was in place and that we were calling the right things. And we know that the interrupt routine is being called because we're calling, immediately after update Sprite positions, we're calling cycle bullet colors. And cycle bullet colors basically just walks through all, where are we doing? Yeah, we're walking through, why are we starting at 8? Because we're starting with sprite color. We're using 2 of the sprites for the tanks, and then we're using 6 of the sprites for the bullets. But I think in this version of the program, we're actually changing the color of all of the sprites. I need to double check that one. But effectively, we go through each color in the color array, the color registers, and then we increment it by 1 using X as our offset into the array. And then here we skip the first 2 sprites. Okay, yeah, so that's essentially what we're doing. So we increment that value, we decrement X by 1, and then, okay, so we're going from the end of the list, we're going back to the top. That's right. I forgot we were doing it that way. So instead of starting from 0, we're starting from 8, which is the end of the list. And then we increment walking that list backwards. And then when we hit the value 1, which is our second sprite, we then skip it. And then we end our routine. So effectively, we're just incrementing the values in those registers by 1 and then stopping. So when our interrupt routine runs, we'll know it's running because our bullet colors will be cycling. And in this version of the program, our bullets should be lined up in the upper left-hand corner because in the interrupt routine, we set them to the position 0, and then its sprite number -2 times 10. So basically we're putting them in the upper left-hand corner over here, well, over here in your screen. We're putting them in the upper left-hand corner, and then we're skipping every 10 pixels vertically. So when we run this thing, make test, here we go. Program does its clear, and then we have our sprites and they're cycling. So what's happening is we are updating the sprite positions, we are cycling the colors, and we know our ISR is actually running, and we're doing this properly. What we can't see here is that we're doing this at the start of a frame, but because it's happening inside the interrupt routine, we know it's happening inside the interrupt and not out of order. So yeah, we are now 30 minutes past the original time. I think I'm going to stop here. Yeah, Tron, a lot of games use this to actually indicate something that was dangerous. And so that's why I'm actually cycling the colors on these, because when we fire one of these things, we want them to look fancy and dangerous. So yeah, this gives us a cheap way of doing that. Yeah, so yeah. The page in the cafe, yes, absolutely. So next time we're going to talk about stage 3. And stage 3, if I remember correctly, we're going to start using joystick input. So the joystick input is kind of a special thing. We'll be using that inside of the game loop instead of the interrupt routine, if I remember correctly. Don't count me on that one. But yeah, the Discord, I will get an interrupt byte. An interrupt byte? Wow, what am I saying? I've been talking too long. I will get an invite and paste it in the chat. There you go. Yeah. Also, yes, the code is available. The code is available here at github.com, jtcans, C128 tanks, like that. So you can follow along with the source code. Just bear in mind it requires Acme, and it requires basically a Linux system to build the source. So just as an FYI. But yeah, thank you for hanging out with me and walking me, or rather, sticking with me as I walk through a bunch of mistakes and stuff. Hopefully next time I will be a little more collected. But yeah, thanks guys. Catch you next time.